Hello, good morning, everyone. Okay, so today we will start a new set of slides. So we will talk about pigeonhole principle. This set of slides, it has only 16 pages, but then the lecture hours is close to 150 minutes. So what does that mean? It means that we are going to talk about some of the results which are which looks very simple in the description because we can describe everything in just 16 pages, but then they are very deep. So in that case, the explanation takes a long time. So let's begin. So we will talk about what is meant by pigeonhole principle, and then we will also talk about the generalized version of this principle, and then we will see also a lot of examples. Okay, so let's begin with this one. Suppose that we have 10 pigeons. So pigeons are birds, usually white in color, but then you can also see a lot of gray and then dark green or whatever pigeons around the campus. And then pigeons, if it is human bred, so they will live in pigeonholes. So suppose that there are 10 pigeons and then we have 9 pigeonholes. In the evening, each pigeon will pick one of these holes to stay. And then what will happen? So one possible scenario is like this. So if you look at this picture, so we have actually, you can see that there are 10 pigeons here around, so there are 2 here, right? So there are altogether 9 pigeonholes. And then we will see that one of these holes will have 2 pigeons or more. Okay. And one possible scenario, so although this is very unlikely, but this could happen is all the pigeons are selecting the same spot. So we may have 10 pigeons in the same hole. What we want to say is that no matter what happens, so in this scenario, we have 2 pigeons in some hole, and here we have 10 pigeons in some hole. What we want to claim is that no matter what happens, we must be able to find a certain hole with 2 or more pigeons. So in one of the pigeonholes, there will be at least 2 pigeons. So how do we show that? So somehow we may say that because in the worst case, so each pigeon will go to one hole, but then after 9 pigeons going into the hole, the last one we must find a hole which we have some pigeons staying there. So we must have 2 pigeons in some hole. But then this argument is not very very formal, because in some parts of this statement, we are saying that in the worst case. So what does that mean by the worst case? So isn't it a worst case? So if this is the worst case, then obviously we have not discussed about this scenario, right? So a better way to argue why this is true is we prove it by contradiction. So we will see how do we show, but in general, we show this particular theorem. We call this the pigeonhole principle. Now suppose that k is a positive integer, and then we have k plus 1 objects to be distributed into k boxes. We can show that at least one of these boxes will contain 2 or more objects. So there are 10 pigeons, and then there are 9 holes. There are k plus 1 objects here, and we have only k boxes. We are going to show this by contradiction. So suppose on the contrary that this proposition is false. So what does that mean? So to make this false, it means that it is possible to have k plus 1 objects distributed into k boxes, but for every box, it will contain 1 or fewer objects, right? So if we assume that this is false, then we are saying that when the k plus 1 objects are placed into the boxes, no boxes contain 2 or more objects. So each of the box contains 0 or 1 object. Now, if each of the box contains 0 or 1 objects, then what does that mean? It means that the total number of objects is at most k. Yeah, we count the total number of objects in the boxes, so it is at most k. But then we arrive at a contradiction. So where is the contradiction? So we have at most k objects, but then we begin with k plus 1 objects. So these two are contradicting each other. So in that sense, we have proven that this principle must be correct. Okay, so we have a couple of examples. So for instance, we can show that there is a number of the form which is consecutive, formed by consecutive ones. So 2 ones means 11, 3 ones means 111. So we can find a number which is just having 1, and then this number is a multiple of 2013. So this set of slides is prepared in 2013. So for this year, this is 2021. So we can also change this example slightly to, we can show that there is a number of the form 1 that is a multiple of 2021. So this is also true. Yeah, how do we show this? Yeah, check out the OCW recording. Another one is, okay, all these examples are very interesting and also not very obvious to think about it. So it would be good for you to try, but then if you find, you have spent a lot of time already, then go to the OCW recording and see the explanation. So another example is, we have 51 integers, and then these integers are distinct integers chosen from 1, 2, 3 up to 100. And then we want to show, no matter what happens, we must be able to find two numbers such that one divides properly the other. Notice that 51 integers is the requirement that we are given here. If we change the problem slightly to, let's say, suppose that we have only 50 integers, then it may not be true for this example. Because if we are choosing 50 integers, we may be choosing the integers from 51, 52 up to 100. So there are 50 of them. In this example, in this choice, we will see that we cannot find two integers such that one properly divides the other. But on the other hand, no matter how we choose any 51 integers, no matter what combination that we are looking at, we must be able to find two numbers such that one divides properly the other. So this is a very nice example as well. And then this one, okay, so let's say we have an equilateral triangle. The size of each side has length 2. And then we are going to put 5 dots inside this equilateral triangle. We claim that we must be able to find two of the points such that the distance is at most 1. Now again, 5 points seems to be needed. If we have just 4 points, there is no guarantee. Because when we are having 4 points, we will be choosing 1 point at the vertex here, 1 here, 1 here, and 1 in the middle of this equilateral triangle. And in this case, the distance between any 2 points must be greater than some number, I don't know, maybe, I don't know how large it is, but then it must be greater than 1. So in that case, 4 points do not guarantee that the closest pair will have distance at most 1. But on the other hand, if we put 5 points inside anywhere, any 5 points inside, then the closest pair must be having distance at most 1 apart. Okay, so again, think about this. So let me give you a hint. So we can always divide this equilateral triangle into 4 smaller equilateral triangles of the same shape. So we have a midpoint here, a midpoint here, and a midpoint here. We join the midpoints together. So we have 3 lines added here. Then this will divide the original equilateral triangle into 4 smaller equilateral triangles of the same size. And then you can start thinking about this problem. And the next one is a super hard problem. Okay. So we want to show that we have a sequence of, so let's say n is a positive integer. So n, let's say, is equal to 2 in this case, but then in general, n can be any positive integer. And then we create a sequence of n squared plus 1 numbers. So in this example, n is equal to 2, we are creating a sequence of 5 numbers, and they are all different. We want to show that no matter how we arrange the numbers, we can always find an increasing or decreasing subsequence of length n plus 1. Now, what is a subsequence? A subsequence is you have a sequence, you can remove some of the numbers inside, the resulting numbers, we do not change their order, will be a subsequence. So for instance, let's say I have 1, 3, 5, 2, 4. If I delete this 5, I will get 1, 3, 2, 4. So this is a subsequence of the original one. If I delete, let's say, 5 and 2, I will have a subsequence of 1, 3, 4. And then this subsequence will have length 3 because there are 3 numbers inside. We call it length 3. And then by deleting 5 and 2, we will have a subsequence which is of length 3, and also the numbers inside, they are increasing. So we can form an increasing subsequence of this one of length 3 by deleting 5 and deleting 2. Also, we can also delete 3, delete 5, and then we will have another subsequence, which is 1, 2, 4. The length is 3, and then it is increasing. Now, in this problem, we want to show that no matter how you arrange the n squared plus 1 distinct numbers, no matter how you arrange it, for instance, I have 5 numbers, no matter how I arrange it, like 2, 4, 1, 5, 3, there must be some increasing sequence, increasing subsequence, or it's not necessarily always we can find an increasing subsequence, but then we can find a decreasing subsequence instead, such that the subsequence is long enough, it is of length n plus 1. So for instance, in this 2, 4, 1, 5, 3, I can find 2, 4, 5. This is an increasing subsequence. For this one, I have 4, 5, 1, 3, 2. Now, if we check everything carefully, there won't be any increasing subsequence of length 3. But then we can, on the other hand, find a subsequence 5 and then 3 and then 2. So this is the subsequence 5, 3, 2, and it is decreasing. Okay, so no matter how you write down the n squared plus 1 numbers, then we can find a certain subsequence of length n plus 1, and this subsequence is increasing or decreasing. Okay, so how can we show? This is a very difficult example. This requires us to use the Pigeonhole principle. For the proof that I know, we will need to know Pigeonhole principle, and also we are going to show this by using contradiction as well. So we need to combine different proof techniques together in order to get the result here. Okay, another example. Now this is also a super hard example. So in this example, we have, okay, so let's say we are listening to the Harry Potter characters chatting with each other. So one of them is Ron, and then Ron is chatting with his classmate. So Ron said, "It was April in my first year at Hogwarts. I've been practicing hard with the spell Wingardium Leviosa, and then I've casted this spell at least once per day and 45 times in that month. So April has 30 days. Each day, Ron has practiced this spell once or more, and then altogether, the total number of times that he has practiced is 45. So we have just this very basic information about Ron's practice. Based on this information, we can show that in some consecutive days, maybe starting from the 3rd day up to the 11th day or whatever, Ron has casted the spell exactly 14 times. Now this is difficult because we are asking things for exact. So it is not like at least 14 times. At least it's easy, yeah, because you can claim that, oh, let's look at the whole month. The whole month has 30 days consecutive, and then Ron has practiced 45 times, so it is more than or equal to 14. But then what we are saying here is that there must be a certain contiguous period that the total number of spells casted is 14. So this is difficult. Okay. So yeah, again, yeah. Perhaps I really would suggest that you go to see if you understand the OCW recording explanation. Okay, so these are the examples of the standard pigeonhole principle. And now we can generalize the pigeonhole principle a little bit. Okay, so first of all, before we talk about this, let me introduce the notation. So this notation is something called the ceiling function. If I have an integer or a real number x, okay, we can take the ceiling function of x to be the integer that is greater than or equal to x, the smallest one that is greater than or equal to x. So, or you can simply say it is rounding up x to the closest integer. So for instance, if I have x is equal to 4, so the ceiling of 4 is still 4 because 4 is an integer already. If you round it up, it is still 4. For 4.1, after round up, it will become 5. For 0.1, after rounding up, it will become 1. How about minus? It is also okay if we define this ceiling function for a negative number. So for instance, minus 1 ceiling is minus 1. Minus 1.1 ceiling, be careful, it is minus 1. We are looking at the smallest integer greater than or equal to x. Okay, so minus 1.1, if you have the ceiling of it, it is going to be minus 1. Okay? Now, so once we know this notation, so we can describe what is the generalized pigeonhole principle. This time we have k as a positive integer. There are k holes. And then we have n objects with big N pigeons. Suppose that the pigeons need to fly into the k holes. So n objects are distributed into k boxes. Then on average, each box, we will say there are n over k things, right? And here we say that at least one of the boxes contain n over k taking the ceiling or more number of objects. So for instance, I have 5 balls. I want to put it into 3 boxes. Then a certain box will have 2 or more balls because 5 over 3, if you take the ceiling, it is going to be 2. Suppose that we have 100 people in our class, then we can see that there are going to be how many? There are going to be 9 or more people. They are born on the same month. Yeah, because we have only 12 months in a year. If we have 100 people, then 100 over 12 is equal to 8 point something. So if we take the ceiling, it will be 9. So we will see that we can find 9 or more people, their birthdays are on the same month. Okay. So how do we prove this? So the proof is still again proving by contradiction. So you can try it by yourself, but need to be careful about this ceiling thing. So you can check the OCW recording for the explanation. Okay, now suppose that we know this generalized principle, so we can solve a couple of examples here. So here, this is the example that I've just mentioned. So this time we have just 80, okay, 80 students in our class. Then in that case, then 80 divided by 12 would be equal to 6 point something, right? So we can claim that if we have 80 students or more in the class, then 7 of them or more, they will be born in the same month. Now, the other example here is consider a standard chessboard. So there are 66 squares, but then we are not doing some standard thing. So we are putting a lot of rooks. So there is a piece of the chess set called a rook. So rook is a piece that can, once you put it in a certain square, it can attack any square on the same row and any square on the same column that it sees. So we claim that if we are putting a lot of rooks in the board, let's say 33 rooks, we put it in the chessboard, then we can find 5 of them or more that they are not going to attack each other. So if I put two rooks on the board, okay, it may not be true. So if I put the two rooks here, maybe one is here, the other is here, then these two rooks are attacking each other. But then we put more rooks in the board instead, 33 of them. Then out of these 33, there is a way that we can choose 5 of them, and these 5 will not attack each other. Okay, so a solution for this one is like this. So let's give the squares some label. So I will make so this is a diagonal, right? This is a diagonal. I'm going to label all the squares on this diagonal 1. I can label all the squares on this diagonal 2 as well as this one. So this is like, yeah, this one, it looks like it continues here. This is the third diagonal, all 3s and 3s here. And then all 4s and 4s here, and so on and so forth. So after this labeling, each square will have a label between 1 to 8. Is that okay? Now, what we can see is that if I place rooks on the squares of the same label, so rooks on labels of 1s, no matter how many rooks we are placing, then they cannot attack each other because rook can only attack horizontally or vertically, but not diagonally, right? So rooks on the same number. So if I put a rook at label 2, and a rook at label 2, and a rook at label 2, so these rooks cannot attack each other. Okay, now we are done. There are only only 8 different labels. We have 33 rooks. So by the generalized pigeonhole principle, we can find 5 of them with the same labels. So these 5 with the same label, then they are not attacking each other. So we're done. And then this is the last page, okay, the last example that we have. Here we want to show that, okay, so first of all, let us describe, okay, so let's say we have a couple of people, we have a bunch of people here, there are 6 of them. Between any 2 persons, they must either be friend or enemy. So we assume that, so we are in a very, very strange case. For any 2 people, they are either friend or they are either enemy. So there is no other, like a third type of relationship. So for instance, these 2 guys, they are friends of each other. These 2 guys, they are friends of each other, but your friend's friend may not be your friend. So these 2 guys could be enemy of each other. Is that okay? So between any 2 persons, they must either be friend or enemy. But we want to say that no matter what happens, among 6 people, we must be able to find 3 of them such that these 3, they are mutual friends, or these 3, they are mutual enemies. We're not saying that we must be able to find 3 mutual friends at the same time we have also 3 mutual enemies. It's not like this. It says that either we can find 3 mutual friends or 3 mutual enemies, or both, okay? So for instance, in a setting that we have 6 people and then they are all friends to each other, then we can easily find 3 mutual friends. So it works. Although there is no 3 mutual enemies, but it works because this statement says that as long as we can find 3 mutual friends, it is correct. As long as we can find 3 mutual enemies, it is correct. Okay? So when we have 6 people, then it must be true for this to happen. Now notice that this is also a very tight bound in the sense that if we have just only 5 people, then this may not be true. Imagine, we can draw the relationship, we can represent each of the 5 people. Let's say we are looking at the example, we have just 5 people. Let us say we represent each of the 5 people by a vertex. So we have 5 vertices here. So imagine we have 5 vertices, 1, 2, 3, 4, 5. They form a pentagon, right? And now let us color the relationship. If their relationship is a friend relationship, we draw it with a blue edge. So we join, let's say let's say these two persons, they are friends, we draw them with an edge that is blue in color. On the other hand, if they are enemy, then we draw the edge in red color. Is that okay? Now imagine a particular scenario. So we have a 5 vertex case. Let's say the outer edge of this pentagon, they are all in blue. So we have a blue pentagon. But in between, all the edges are red. So we have a red star inside. Is that okay? So we have a pentagon in blue color, but then we have a red star inside. So I hope you can imagine my drawing here, although I am not drawing here. Then you can see that we cannot find 3 mutual friends. Also, we cannot find 3 mutual enemies. So what does that mean? So if we have just 5 people, there is no guarantee we must be able to find 3 mutual friends or 3 mutual enemies. For this example here, it says that when we have 6 people, the scenario is different. We can always find, no matter how the relationship, how complicated the relationships are, we can always find 3 of them, such that they are enemies, mutual enemies, or they are mutual friends. Okay, so this is also a very interesting example. So it also requires the proof by using the Pigeonhole principle together with the contradiction proof. Okay, so yeah, think about this and then yeah, and then check the OCW recording for the explanation if you have spent a lot of time already. Okay, so that's all for what I want to show today. Okay, so thank you very much. Yeah, I hope you like it. Yes, so I will be sending out the assignment 3 for you today, and then we will talk about some of the questions for the Pigeonhole principle there during the next tutorial. Okay, that's all. Thank you, and then see you again next Monday. Okay, bye bye. Thank you.